All right. So we're going to pick up with chapter 13 today, chemical equilibrium. And we're doing chemical equilibrium now after chemical kinetics, because the equilibrium concepts piggyback on kinetics. In other words, it'd be more difficult to understand equilibrium until we had an idea of what kinetics were. So under what conditions do we reach equilibrium? And this is by way of definition. If during a chemical reaction, you reach a point where the concentrations of the reactants are stable, they're constant, and the products are also constant over time. That's what we mean by equilibrium. There is no apparent macroscopic change in concentration for a given reaction. Now we know that on the subatomic level, there's still frantic activity, but the appearance on the macroscopic level is that there's no activity. So this is what it looks like for this particular reaction, where we have nitrogen gas and hydrogen gas combining to form ammonia. So at time 0, we have no ammonia formed. It's 0 concentration. We have a little bit of nitrogen. Based on the balanced equation, we have 1 mole. But we have 3 moles of hydrogen at the beginning. So over time, both the hydrogen and the nitrogen decrease in concentration, and the concentration of ammonia increases until we reach a certain point of time when the concentrations of all 3 of these appear to be constant, unchanging. Now, that equation, I'm going to leave out the gas part. That equation produces ammonia from nitrogen and hydrogen. But as soon as you start getting some of the ammonia produced, it wants to go back the other direction. So that's why we have a double barbed arrow like that. Because it says that as you build up more and more of this, the pressure, the reverse pressure to form reactants from products builds up against it. So you reach a point where the forward rate is equal to the reverse rate. So that's why we need to know something about reaction rates, because the products tend to want to make reactants again. And then when you reach the equilibrium, we might say this forward rate, let's see, forward is equal to the reverse rate. And this is just another way of representing it. If this represents the forward rate in the beginning is very high because you have relative high concentrations of reactants. But as you decrease the amount of reactant, the rate drops off. You don't go as fast. And at the same time, you're creating product which tends to have its own rate in reverse. And at some point, these two meet, the forward rate and the reverse rate meet one another, they're equal, and at that point you have equilibrium. So what happens in this case when we're reacting carbon monoxide with water? We're going to produce hydrogen gas and carbon dioxide gas. Now, if this reaction were taking place in an open vessel, once you produce these gases, they're just as likely to go, they're gone. So this reaction has to take place in a closed vessel where the products are forced to remain in contact with one another so that the reverse reaction can take place. Now, this concept, we'll give it a name later, but for now, what happens if you add more? Let's say, first of all, let's say we've reached equilibrium, where the forward rate and the reverse rate are equal. So you have some reactants and you have some products, enough of each, so that those two rates balance. Now, at that balance point, what happens if you add more water to the flask? As long as there's carbon monoxide available, that extra water that you add is going to react with that carbon monoxide. So you've introduced an unbalanced situation by adding a little bit more of this reactant. And that way, the reaction will proceed faster in this direction than in the reverse until you reach another equilibrium point. And once you reach that equilibrium, it will stop. You will have a balance between these two once again. Similarly, if we add hydrogen to the flask, that will unbalance it in the reverse direction. And the reverse reaction will increase until we reach a balance in the forward and the reverse reaction. Now, the description of an equilibrium situation was given to us by two Norwegian scientists in the middle of the 19th century, Weg and Goldberg. And they were just looking for a way to describe what was going on in a reaction and what the conditions were for equilibrium. And they came up with an expression. They called it chemical dynamics versus chemical statics. Chemical dynamics would be what we call kinetics now. And what they call chemical statics, we call equilibrium. But the important takeaway from here is the expression they came up with. And this is always expressed in terms of concentration. When we introduce variations on that theme later, it's always with keeping in mind that the equilibrium is based upon concentration, not necessarily upon absolute amounts. So this is the expression they came up with. And I don't know why I keep this slide, because I prefer writing it this way. Say if you have one reactant, two reactants, yielding two products, then the balanced equation, we would say, has a coefficient there of A, B, C, and little d. Now, the expression itself is going to be equal to a constant. That's our K. And this is the equilibrium constant. And with it written this way, you say the concentration of C to the power of the coefficient little c times the concentration of D times the power of little d. So the products always go in the numerator, and the reactants go in the denominator. The little a and the little b. That's standard form for an equilibrium expression.
So what's the difference between that and then what's on the slide? Is it just because they're using different coefficients?
Yes, they're using different letters for the coefficient, and it just doesn't. This way you know where each one came from.
Okay.
That's why I like that one better. And notice some conventions. Besides the power being equal to the coefficient, the concentration at equilibrium is in square brackets. Okay. That's convention because later on, we want to use an expression that's not at equilibrium. And when we do that, we use parentheses. But we'll get to that later. Another thing that is typically not done is units are usually not given for that value.
Okay.
The reason being that the range of expressions for balanced equations are so wide and varied that giving the units would take up more room than the value itself. So we just have to be careful that when we're writing the expression, we use the proper units, and we be sure that we've incorporated the correct powers. And then when we do the calculations, we get a number, and these numbers are listed in either articles, published articles, or in reference manuals. So you can look them up. And the one factor, actually two factors, that determine the value of K is temperature. So if you change the temperature, the equilibrium value is going to be different. Right? So this K value is only constant if the temperature remains constant. And the other is what units are you using here? If you change the units of concentration, then the K value is going to change. So you may have to specify these concentrations are in molarity, perhaps, and that's the most common. The two most common units of measure are molarity and partial pressure. So if you have an experiment where all the components, both reactants and products, are gases, many times that concentration will be expressed in terms of partial pressure, like atmospheres, for each of the components. Otherwise, molarity is the more common concentration. Okay. So what do we do if we have a balanced equation? And we want to say, remember when we were doing Hess's law, where we're combining equations into an overall equation? You remember that?
Yes. I think so.
Yeah. So when you, I think it had to do with heats of reaction, enthalpies. So when you combine equations and you have the enthalpy out here, you just added up the values to get the enthalpy of the overall reaction. Okay. In the case of equilibrium constants, though, when you have to invert an equation before you add it to the others to get where you're going, that changes this value. So if you invert it, now the reactants are on the product side. So what that does is it just completely flips it. So the value of K for an inverse reaction, say if we were to write this one, like then the value of K over here would actually be the inverse of that K. I should say, the new K is equal to the inverse of the old K. Simply because we reverse the order. Now, this is the product side, so it goes on top, and the reactant side goes on the bottom. So that it just flips it, yeah. Oops. There we go. So that's what you do when you have to flip the equation. When you multiply by a factor, let's say we have to multiply this whole thing by a factor of 2 in order to, before we can combine it with other equations. What then does that do to the K value? Well, look what it does to the coefficients. It doubles each of the coefficients, right? So we have 2 here, 2 here, 2 here, 2 there. Right? So if we factor out that 2, well, I'll just write the whole thing again. If we factor out the 2 from that change, where does it go? It goes out there, right? So when you multiply through by a constant through the entire expression, then the new K is equal to K to the power. In this case, it would be K squared. So when you multiply the whole thing through by a factor here, that factor becomes the power of K, the old K, to give you the new K. All right. Those are the common manipulations that you may have to do before combining equations. And the reason you have to do that is when you combine those equations, you're going to have to combine the K values as well to find out what's the K for the final one. Okay, K is constant only for a constant temperature. If you change the temperature, you change the equilibrium. Okay, so let's see. I'm going to have to erase all of this. There's also a distinction that we need to make between equilibrium constant, which is represented by K, versus equilibrium position. The equilibrium constant is just what that, it's a constant. Now, how do you get that constant? Well, you ratio the concentration of this one to that power times this one to that power, and you ratio that product in the form of a quotient with these in the denominator, A to the A power times B to the B power. Now that ratio establishes a constant value as long as the temperature is constant. But if we do something like we did before and add some component after equilibrium, it makes it shift. At that point, the concentrations that we started with in the equilibrium place will change. In other words, if we add a reactant, only part of it is converted to the product, not all of it. So that gives us a new position, which means that we will have the same equilibrium constant at work, but if we add A and only convert part of it over here, that gives us new concentrations here and a new concentration here because we didn't use all of it. But if we didn't add any of that, we're going to use more of this, so it decreases that concentration. Those shifts in concentration are behind this idea of equilibrium position. So the equilibrium position can be at much different concentrations for the same type of reaction. For the same balanced equation, we could have different concentrations that give us exactly the same K, but different positions. So they could be low concentration, high concentration, medium concentration. They still give us this same value, but at different positions. Okay. I wanted to make that distinction so that when we talk about it later, it won't be a surprise. Okay. So K, the general form K is the equilibrium constant, but very often the K has subscripts applied to it. And these subscripts are specific to different types of equilibrium. If we just say K or KEQ, those are fairly generic. And these are just equilibrium constants, which usually represent concentrations in molarity. If we're talking about this one special one, KW is the equilibrium dissociation constant for water. So in solution, water will do one of these things. It will react with itself and produce the hydronium ion plus the hydroxyl ion. It's often written, though, like this. More often you'll see it like that. But there's a constant associated with this. If you have pure water, it will dissociate into hydrogen ions and hydroxyl ions and leave mostly water behind, but you'll have some of this. And you can write an equilibrium expression with concentration of this times concentration of that in the numerator. But you don't put liquid in. Well, we haven't got to that slide yet. Okay. I'll just give it to you now. We would be tempted to write this, right? Right, in the numerator, and this in the denominator. But for pure substances, they don't count. They're never put in the expression. So if you have a solid, like we have a precipitation reaction that forms a solid, that is not included in the reaction equilibrium expression. Pure liquid here, that's not included either. So the only expression that counts is that times that.
It would just be K2 equals.
KW equals hydrogen ions times hydroxyl ions. Concentrations, that's it.
But that's only for pure substances.
Right. Solids and pure substances like the liquids. So that's a special expression for the dissociation constant for water. We have another one for acid dissociation constant. So if we had, let's see, acetic acid it's going to produce a proton plus the acetate ion. Okay. Now this will be aqueous. All of these will be aqueous. So that one is included in the expression. So Ka for this one will have this one times that one divided by this one. Right? It's not a pure substance, it's in solution. Right? So it has a concentration. Each has a concentration, and they will be included in the expression for an acid dissociation constant. Solubility product. So if we have a solid over here of something like, let's see, silver chloride, we'll make silver ions in aqueous solution plus chloride ions in aqueous solution. For this one, the solubility product would be just this one times that one. There's a solid, pure substance, we don't include it. So it'd be just this concentration times that concentration is equal to the solubility product, which is an equilibrium constant.
And that one's like the water dissociation.
Yes. Okay. Use a similar rule. We're going to do this one next to the last lab. We're going to do one involving complex species formation. So we'll talk about that in more detail later. But they're all based upon equilibrium. They just have these subscripts that are reserved for those particular types of reactions. Now, if your concentrations are in terms of partial pressures, so you have all gases in your reaction, then you may have a case of P. And when you see a case of P, you know that the concentrations are in partial pressure. And that's usually atmospheres. Okay. So terminology, let's see. This is what the difference would look like if for this reaction where you have the nitrogen and the hydrogen making ammonia, if we used molarity, the expression would look like this one, where that would be squared, this would be the first power, and that would be the third power, square brackets. But for this one, the only reason that the parentheses are in here is just to separate the powers from the partial pressure. Sometimes you don't see those parentheses. You would just have the power up here. Well, they wouldn't have one there, 3 here, as a superscript. And we would specify the K as case of P because these are in partial pressures. Now, these are going to give you different values because they're different units of measure. Right? So this K does not equal that case of P. Okay. They're related, and maybe we'll get to that too. But say we had, at a given temperature, we reach equilibrium in a closed vessel, gas, gas, gas. And these are the partial pressures of each of the gases in there. So we would just take this one here, square it, and divide it by this one to the first power times this one to the third power. And that's what we're doing here. And our case of P then would be 3.9 times 10 to the 4th. Now, if we had, these were in atmospheres, that would be atmosphere squared on top of atmosphere times atmospheres cubed. So the units of measure here, if they were quoted, would be atmosphere squared divided by atmospheres to the fourth, right? So that would be, these two would cancel, leave us 2 in the denominator, which would be atmospheres to the -2 power. I mean, we don't put that down here, but that's what it would actually be. And all we would have to do is have a reaction of 4 gases, right? And then we would have a completely different unit of measure for our case. So that's just an illustration of why we don't put the unit on there, because they just run wild with themselves. You just have to be careful that you do all the calculations correctly, and then the units at the end of the solution to your problem will come out right. Okay. Now, I said before that the K value in molarity is not equal to the K value in partial pressures, but they are related to one another. And they're related by this equation. So the K sub P equilibrium constant is equal to the K constant with molarity. This is partial pressures. This is using molarity, times the universal gas constant times the temperature in Kelvin. And all of this to the power of delta N. So the question is, what do we mean by delta N? Delta N is the sum of the coefficients of the gaseous product minus the sum of the coefficients of the gaseous reactants. So for this one, where we have nitrogen plus hydrogen in equilibrium with ammonia, N would be products minus reactants, 3 minus 1, right? 3 and 1. So the coefficient would be minus 4 plus 2 would be minus 2. So in that case, delta N would be minus 2. And all you would need to do then is establish your temperature, whatever your temperature is in Kelvin. Then R is your constant, the gas constant, the one that incorporates atmospheres, which would be 0.08206. And take that to the -2 power, then you can multiply it by K, and that will give you K sub P. That's how they're related. If you knew K sub P and you wanted to find out what K was, it's like any other equation. If it's one unknown, you can solve it. So you would have a value here, a value there, a value there, a value there, solve for this one. Okay, so we have an example. In this case, we found that K sub P is this value at 35 degrees centigrade, which is 308 K. And here's our -2 power, 2 minus 4. And then we're just solving for K. So K turns out to be this. And K is in terms of molarity. I'll leave that there for now, just in case. Any questions so far? All right. So we've used these terms before, homogeneous versus heterogeneous. Homo means same. So a homogeneous equilibrium is one in which all of the reactants and products are in the same phase. So that would, an example would be this nitrogen plus hydrogen yields ammonia. They're all in the same phase, so that's a homogeneous equilibrium. This one would be an acid dissociation. Would be hydrocyanic acid in aqueous solution dissociates to make one proton and one cyanide ion in aqueous solution. Those are all homogeneous because they're in the same phase, the aqueous phase. If we have different phases, in this case we have potassium chlorate, solid, heated up and you get potassium chloride plus oxygen gas, that's a heterogeneous equilibrium. And in this case, your equilibrium expression would only have that component in it right there, because that's a solid and that's a solid. We don't include solids because their concentration doesn't vary. I mean, if there's solid there, it's for all intents and purposes 1. Or this, what have we done here? Oh, we've split the water molecule into hydrogen and oxygen. Right? Maybe run an electric current through it. So now we've got gas as product and liquid water as reactant. This is a heterogeneous equilibrium. But again, when we write the equilibrium expression, we only include the gases because water is pure. It's a pure liquid, just like solids are pure. This liquid is pure. So the equilibrium expression will only have hydrogen gas and oxygen gas in it. Oh, this is just more of the same. I've already said this before. And why? We don't include the solids in the equilibrium expression because their concentration does not change during the reaction. I mean, you might have less of them, but the concentration hasn't changed. No, it's just a smaller glob of the solid. Concentration doesn't change, only the amount. Okay, let's see if we can derive some qualitative information from the K value. So if the K value is extremely large, much, much greater than 1, what does that say about the equilibrium position of the reaction? Concentrations of reactants versus products. Think about the K. What does K mean? Well, it's got reactants over products, right? In some form or fashion. So if the value is extremely large, if K is a lot larger than 1, does it favor reactants or products? Oh, you let me get away with that. It's products. Product divided by reactants. Okay, now we can answer the question correctly. Products divided by reactants. Okay. Did I confuse you?
Yeah.
Okay.
When you wrote it out, I was like, okay, it's
That's
something different.
Yeah, the reason you're confused is it was wrong.
Okay.
It's products divided by reactants. Okay, now, if K is very large, greater than 1, that would favor the products. Right? So we have a lot more of this and a lot less of that. And vice versa, if we have K that's a lot less than 1, that means that we form a very small number, which means large denominator, small numerator. So very small products, very large reactants. In other words, that equilibrium situation means that there's not much product formed at that temperature. Very low reaction rate in that direction, very high reaction rate in this direction. That's what the K stands for. It gives us some qualitative information about the reaction. Now, if it's pretty close to 1, this is a really big rule of thumb. If it's close to 1, then there's a relative balance between the two. Not exact, because it all depends on the reaction, and the powers that are involved. So if you have different powers here than you do on that side, it's going to throw this off away from 1, but within a wide margin, it's going to be close to 1. But we can say that if it's extremely large, larger than 1, or extremely smaller than 1, we can't say that it favors either reactants or products. The other thing is, if K is very large, then the reaction goes essentially to completion and leaves almost nothing behind. There's such a low concentration that it's ignorable. If you want the type of reaction that gives you all of the products you want, then that's what you want to see, a very large K. If you have a reaction with a very small K, that means it favors these. So in that case, the reaction that you would look for going to completion would be the reverse reaction. Flip it. That changes this one to that one. And then you would look at that these as reactants and this is product. That one would go to completion. Okay. Here we go. This is just to see if I didn't confuse you too much. If the equilibrium lies to the right, the value of K is
Larger.
very large. Yeah. And if it lies to the left, it's very small. Now, suppose we're not at equilibrium. What do we do with that situation? Can we predict which way the reaction is going to go? Well, before we do that calculation, we could say, well, if we mix A and B in a vessel, and that's it, then it's easy to predict it's going that way. It's going to make some product. Even if it's just a small K, it'll make a little bit of product. Or if we just put C and D in there, it's going to make a little bit of A and B. Right? So that's easy to deduce. If you're only given reactants or only given products, you know which way the reactions go. But what if we're given a concentration of A, B, and C, D? Then how do you tell which way it's going? We calculate what we call the Q value. So we treat the concentrations that we're given in the same way we would an equilibrium expression, only instead of a K, it's a Q. So we'll have a concentration of C to the C power and D to D power. There's our parentheses instead of square brackets because we're not at equilibrium. And there's A to the A power and B to the B power. And we get a value that we recognize is not at equilibrium. But we want to compare this to the K. Say we know what the K value is, then we calculate the Q value and compare it to the K. And that will tell us which direction the reaction is going to go. These are called initial concentrations rather than equilibrium concentrations. Okay. So if the K is equal to the Q, we know it's at equilibrium, right? Okay. what if the Q is greater than K? It's this way. If Q is greater than K, what does that say here? That says that we have more products than we need and less of the reactants. So if Q is greater than K, then that means we have more of this, less of this. That means we have more of that than we need, and we're going to head that direction. So if Q is greater than K, we're headed to the left, as written. Okay, that's why it's important if you're going to say, well, the reaction goes left or right. If you don't have an equation to work from, left and right means nothing. Because if it were flipped, your left and right explanation would be flipped.
So it's going to depend on the way that the equation is written out.
Right. So the reason I'm emphasizing that is when you guys are doing the lab next week with equilibrium, you're going to have reactions and you're going to describe what you see happening. And then in terms of the reaction chemistry or the balanced equation, you want to say the reaction tends toward this direction or that direction. Well, if you say right and left and you don't give me an equation to go by, then I don't know what you mean. Right? So you need to put an equation in there before you say left or right. The only exception to that is if the question itself says the equation is this, then you can say it goes left or right.
Oh, but it has to have the equation.
Oh, yeah.
Which direction to go.
Yeah. Or you could say it tends toward products or it tends toward reactants. Let's see. So that's with Q greater than K, we're going this way. Right. If Q is less than K, for the converse reasons, it would tend to the right. Because if Q is less than K, that means we have too few products and too much reactants. To make Q less than K, you would need less of this and more of that. So that means less of this, more of that, means that direction. Okay, so here we have a real world example. I think I can do away with the A, B, C, D now. We're going to start using real equations. So for this reaction, we have the ferric ion, Fe3+, reacts with the cyanide ion, and you guys are going to do this reaction, is in equilibrium with this complex ion. So what would the expression be for that one, for equilibrium expression? And this is actually one where you would have the little f, the equilibrium constant of formation. We're taking this ion with that ion and making that ion. So our equilibrium expression then would be concentration of that. Right. And since there are no powers here, everything's to the first power. Well, it's 1, 1, and 1. And then on the bottom, we would have the reactants. Okay, so that's what the expression would look like, the equilibrium expression for that equation. And we're given, in this case, okay, this concentration of iron 3+, this concentration of thiocyanate ion are mixed at a certain temperature, and at equilibrium, the concentration of this equals that. Okay. my notes. I don't want to throw the slide up there until I know we're going that direction. Yes. Okay. So I should have written this out to the side. Let me just write it again. All right. So we're going to introduce a technique called the ICE table. And ICE stands for what are the initial conditions, concentrations here, here, here. What change takes place for this one, for that one, for that one. And then what is the equilibrium situation for each of the others. That's what ICE means. Initial, change, equilibrium. So the initial conditions for Fe3 plus, 6 molar. And for a thiocyanate is 10 molar. What concentration for this one? It just says that these two are mixed together. Then at equilibrium, we have a given concentration of this one. So in the beginning, it's that situation where you don't have product, you only have reactants. Right? So we know which way the reaction is going to go, right? It's going to that way. Now, what's the equilibrium concentration? Well, it tells us the equilibrium concentration for this one is 4 molar. Right. So that's given information. Now, what do we need to determine this value? Because that's the question. What is the value for the equilibrium constant? We need to know this one and this one because we already know that one. Okay? What change has taken place right here? We've added 4 molar of that right there. Right? So that gives us this one. The change here is an addition of this species. So what did that do to these guys? Well, they're 1 to 1 to 1, right? So for every one of these that shows up over here, we lost one of those, didn't we?
Yeah.
Right. So we actually lost 4 molar here. So that means we're left with 6 molar. Okay. And for every one of those, we lost an equivalent amount of this one. Exactly. So that leaves us with 2 molar here. So now we have our equilibrium values. We can do the calculation. So the K would be 4 on top. Well, I should be consistent. That's equilibrium. So it's going to be 4 in square bracket. And this is going to be 2 times 6. So it'd be 4 divided by 12, right? 4/12 would be 0.3?
0.33.
Yeah, 0.33 is the K value for that reaction. So we were given this one, and that one, and we use this ICE table to deduce the other parts that we need. They don't always come like that. Sometimes they might come like, you might be given this one, and of course, that one, and you might be given this value and say, what are the concentrations of these other guys? So it can come in several, but the ice table is a very powerful technique, and we'll use it many times over, not just in this chapter. So don't forget it once we leave this chapter. Okay. So this slide gives you the ice table set up just like we did here, and then the calculation produces that value. We'll go at 3 decimal places. Now that we know what K is, suppose we change the situation. Say our initial concentration of Fe3 plus is 10 and thiocyanate is 8. So let's go in here. Use the same ice table, but with different values. So now we're going to start off with 10 here, 10 molar, and 8 molar here. And again, none of this, right? Okay. So let me be sure I know where I'm headed. Yep. So since we don't have any equilibrium values down here, we can't say how did it change. So we're going to have to use a little algebraic manipulation. We're going to say, since there's none over here, we know it's headed that direction. We know it's going to produce some of this. We don't know how much. It's going to produce some. And if it produces some like that, since they're 1 to 1 to 1, it had to lose the same concentration here and there. Correct? Okay. So now we can do the change then is going to give us X there. It's going to give us 8 minus X here and 10 minus X here. So with our expression, we can say this 0.33 is equal to this value, that value, excuse me, product. X on top divided by this one times this one. Okay, so now we have an equation in one unknown. And we can solve for X. Now, what was the question? At equilibrium, what is the concentration of this ion? So we by accident set it up correctly so that when we find out X, that's the answer. Sometimes when you set them up, if you choose X, not incorrectly, but imprudently, you may have to take that X and do a calculation to find the answer. But for this one, X is the answer because it fits right there. Now, what do we do with that calculation? There we go. Right, solve for X. So, the problem is that this is X times X. This is a binomial expansion, which is going to give you a quadratic equation, which means that in this case, we have something X squared and then minus something X plus a constant equals 0. Then we have to use the quadratic equation solution to get answers. And we have to decide, because the quadratic always produces 2 answers, remember? We have to decide which one makes sense. So if we do it like that, and we expand this binomial, and then do all the jump through all the hoops here, and produce this binomial, and then use this solution, which I keep on the back of my calculator. Then you fill in the values for your ax squared plus bx plus c equals 0. Fill them in here as prescribed by the equation. Then you get two answers, 1599 and 5. We have to decide which one makes sense. Well, if you start off with 10 and 8 here, there's no way you can end up with 15.99 over here because they're 1 to 1. Right? 15.99 subtracted from that would be a negative number. Negative number. So we know 1599 is wrong. The only one that makes sense is 5. So x equals 5 molar. If we did all our calculations right, then the concentration would be in molarity. And that would be 5 molar here. Now, if we wanted to know how much we have left over here, we just subtract 5 from that is 3, and 5 from that is 5. And at equilibrium, you have 5, 3, and 5 here. Before, we had different values here, didn't we? They were at equilibrium, but it was a different equilibrium position because the concentration set is different, right? But the equilibrium expression is still honored. Now, there's a shortcut that sometimes you can take. If this value is extremely small, then you know that you're going to produce very little product, right? We just said this is very small, like 10 to the minus 3. This is only 10 to the minus 1, but if it's 10 to the minus 3, then we know it's going to produce very little of that. So in that case, we can say this x is much smaller than 10, ignore it. This x is much smaller than 8, ignore it. So it'd be 80. Then bring your 80 over here times that, and that would be your x. But in this case, if we tried that, the value would be way, way off because this value is not small enough. Okay. We're doing good on time, I think.
It's only 3 o'clock.
Okay. In this case, what do we have? 6 molar, 6, and we're going to recalculate that one again. Okay. So we're going to start from scratch. I'm not bothered doing this one. I'm going to make a different point. It's the same calculation. Okay. You just end up with a different value, a different equilibrium position. Okay. Right. This one's going to end up being 3, I think.
But we'll just do it the same way.
Exactly the same way. Okay. Where you don't know what the change is, but you do know it's going that direction. That's important. If you know it's going that direction, then the change is going to be plus x. If we had some of this and some of that, then you would have to do a Q calculation and see, is it going this way or that way? If it's still going this way, then you got plus x. If it's going back this way, then you're going to have minus x here and plus x over on there. Okay. As always, write the balanced equation, then the equilibrium expression, then set up your ice table and list your initial concentrations. If necessary, calculate the Q to find out what direction you're going. You may have to include an unknown value. The first example we did, we didn't have to.
No,
because, right, we had a real value down here to tell us what the changes were. But if you don't know, then you have to substitute some unknown. And substitute that, once you find your equilibrium expression, substitute that in here and solve for the unknown. And then check your calculated equilibrium value to see if it makes sense. So if you calculate a value over here, then use it as we did over here to find out what that one is, what that one is, what that one is, plug it back into your expression and see if it equals that value. If it does, then you're good. Also, there's a rule of thumb. Are we going to get to that? No, it's not in these slides. I don't understand that. If we were to do that shortcut and say X is going to be so small we can ignore it, and we come up with a value. Say instead of, what was it?
5.99.
Okay, 5 is the value that we calculated the exact way. If we were to do it saying that X is too small, then we would say it was 10 times 8 is 80 times 0.333. 80, 0.333. So that would be 26.6.
10 times 8 and then times 0.33 or divided.
Yeah, because this would be, that would be so small that we would say that's 10, and this would be 8 times 80. 10 times 8 is 80, and then multiplied times this would equal our X. Right? So that would give us 26.6. Well, we know that one's wrong, right? If 1599 is wrong, 26 is wrong. But suppose, let's just for argument's sake, we came up with a value that was 5.10. Is that close enough to accept?
Yes.
There's a 5% rule. So what you would do is you would plug that X into your expression, the values for X. Say if we started off with 10, 8, so it'd be 10 minus 5.10, and then 8 minus 5.10. And then we would have up here 5.10. Calculate that value. Let's say 5 on top, 10, 0, minus that. That would give us 0.352 as our calculated K. K prime. So this is our true K. This is our calculated K using whatever approximation. Right? Are you with me so far?
Yeah, mine just spit out 3.01, 3.018. So 0.312.
Let me do it again. Is this right?
5.01.
X. Yeah, 5, 10 minus 5. This would be 4.9, right? And this would be 2.9. Right? So 5.10 divided by 4.9 and then divided by 2.9. I still get 0.39. We try it one more time. Yeah, 3.59 or 0.359. You still having trouble?
Well, it's still spitting out 3.01. 5.10 divided by, and then I just went ahead and,
Divided by this?
yeah, divided by 4.9 times 2.9.
No, divided by 2.9. They're both in the denominator.
But,
Oh, say this one times that one?
yeah.
Then divide that into 5.1. Okay, so now once you get this calculation from your approximate value, this is just for argument's sake. Say we used an approximation and ended up with this value. Then we do the calculation of what would the K be if we use this value. That's the whole point of this. Then we compare the two and say, is this one within 5% of that one? So we would have to say 0.359 minus 0.333 and divided by the accepted times 100. So 0.359, subtract 0.333, and then divide by 0.333 times 100. So that's 7.8%. So it fails. It's greater than 5%. Right? So that approximation is wrong. Now, there are a couple ways to deal with it. If you do that approximation and you end up with the wrong answer, you can always go back and use the quadratic. Right? And that'll give you the exact answer. The other way is to do successive approximations. In other words, if we come up with this value and we have our expression for, say in this case, x over 10 minus x times 8 minus x equals 0.333. Then what you can do is you can plug in this value here, there, and there, then solve for x again. And what it'll do is it will gradually, over 2 or 3 steps, if you repeat this, get you closer and closer and closer until you are below 5%. Yeah. Successive approximations is what that's called. Sometimes these expressions are so complex, the quadratic won't work. It might be a cubic, or it might be a 4th power polynomial that you have to solve. And those become unwieldy even for computers. So then you're forced to go to successive approximations to find the answer.
So would it still be, even if it was like just so small as to 5.1%, would it still, I mean, would that?
Well, okay, test taking technique, right? If you're pressed for time and you find that that answer puts you closer to one of the answers that's given, I'd go with it. But technically speaking, if you are over 5%, then you should do the approximation or do the exact quadratic if it's available. Okay. So I need to put a slide in there on that 5% rule. Okay, there we go, there we go, there we go. We've done that, done that. Now, consider the reaction. Find the equilibrium concentrations for all species. All right, we're not going to do that. It's going to take forever. But you set it up just like before. You're starting initial concentrations. X is your unknown. If you're going to be, well, maybe we should do 1. Yeah, let's do 1. because this is going to involve the calculation of Q. Yeah. Because we are given concentrations for each one. That means we're not sure which direction it's going. So we'll just do the first one. And 5, these are initial concentrations, and 1. So then we want to calculate Q as 1 divided by 9 times 5 equals 1 divided by 45. 0.022, which is much less than K. So less than K means that direction, right? Greater than K means this direction, right? That's because our Q value says that this is very small, which means it wants to go that way. So now that we know which direction it's going, we're saying we're going to add more of this one. So we're going to have to add some of that, and we're going to lose, since it's 1 to 1 to 1, we're going to lose an equivalent amount of that one. So now our equilibrium expression is 9 minus x, 5 minus x, and 1 plus x. So now we can write our expression as, let's do away with that one. And plug in the values for 1 plus x divided by 9 minus x, 5 minus x equals 0.333. All right, we're going to have to muscle this one through. So 9 minus x times 5 minus x, we have to expand that polynomial. So it's going to be x times x is x squared. And then x times 9 minus 9. And then a minus 5 is minus 14x, right? I'm expanding the polynomial.
Okay.
So it's this one times this one, that one times that one, which is 45. And this one times this one plus this one times this one, and both negative. So they're negative 14. 5x, 9x. Okay? Just take you back to algebra.
Yes.
Okay, so now we're going to have 1 plus x is equal to this whole thing times that value. So this is going to be 0.333 x squared minus 14 times 0.333 is 4.66 minus 4.66 x, and then 0.333 times 45 is 14.99. I can do better than that. Okay. So now, in order to solve a quadratic, the quadratic has to be equal to 0. So that means this whole amount has to go on that side. So this 1 becomes a negative 1 and reduces this one by 1, right? That negative, subtract 1 from both sides. So that makes this one 1 less. And this one becomes a negative on that side, which makes it like that. Okay? So now we have that expression, and we have to plug it into our quadratic. So x equals minus b, so minus b minus 5.66 plus or minus square root of b squared minus 4 times a times c, all divided by 2a. Okay? Then we just have to solve that equation. So x is equal to I guess I'm going to have to do it. All right, so what is this square root expression? So 566 squared is 32.04, and then minus 4.333 times 13.99 times, subtract that, and then take the square root. Okay, so this whole expression here is 3.66. So that means one value of x is this, that makes it a positive. 5.66 plus that value divided by 0.333. So one possibility is 14.0, or 5.66 and 3.66 minus, then divided by, this is 3.00. Okay? So it's either 14 or 3. Well, it can't be 14 because it would completely use up all of these. So it's got to be 3 for the first one. So x is 3. That means that for the first one, this value is equal to 4, 3 plus 1. This value is equal to 2, and this value is equal to 6. 6, 2, and 4 is the first one. Okay? Now if we go through that whole rigmarole for the others, those are the answers. So it can get complicated really fast. That's why when you work these problems, well, just like all the other chemistry problems, you need to be very methodical about your process. And continually asking yourself, is this making sense? Okay. Where is this one going? Do we need to bother with it? We got time. All right, so let's make room for a new equation. All right. Oh, we need to go.
Just a point break.
Okay. Okay. So here's another example of an equilibrium expression for ammonia yielding okay. The difference between this one and the previous one, the equation's flipped, right? Maybe it's, is it flipped? Or did we use this one before? Yeah, the equation's flipped. So in this case, we're going to treat the equilibrium as ammonia is a reactant, and nitrogen and hydrogen are products. Okay, so what is it telling us? A 2 mole sample of ammonia is introduced into a 1 liter container at a given temperature, and ammonia partially dissociates. Okay, so the initial conditions: 2 moles of ammonia in a 1 liter container. So what's the concentration? No, the concentration of ammonia. 2 moles. 2 moles in 1 liter is 2 molar, right? Moles per liter. So that's given. And at equilibrium, 1 mole of ammonia remains. So at equilibrium, we have 1 molar because the size of the container didn't change. So we have 1 mole left over. Okay, calculate the value of K. Let's see, can we do it? All right, so what was the change from here to here? Well, we lost 1 molar concentration of ammonia, right? That's what it took to give us 1 molar. So when that happens, and the initial concentrations here are 0. When that happens, wait a minute. That equation is not balanced, is it?
It is not.
Yeah, 2 nitrogens, 2 nitrogens. Now it's balanced.
No?
It's not. 2
Oh,
nitrogens,
maybe, okay.
6 hydrogens. Now it's balanced. Let's see if that made a difference. If we had 2 molar here and we went to 1 molar here, we had to lose 1 molar. That didn't change. Now, what's the change? If we lose a molar here, how does it show up over here? Well, for every 2 of these, 1 of those. So this adds a half molar, right? We went from 2 to 1, 1 to half.
Okay, because you're split.
2,
Okay.
yeah, 2 to 1, 2 to 1. If this is 1, that's 2. And in this case, if that's 1, how much is 3? 3 times 1 is 1.5 molar, right? Okay, now we can determine what's our equilibrium concentration. Now we can calculate our K. So our K is going to be the concentration of nitrogen times hydrogen cubed divided by ammonia squared. So the concentration of nitrogen is half. And hydrogen is 1.5 cubed. And ammonia is 1 squared. So let's see if we can calculate that one. 1.5 meter cubed, and 0.5 times, and then divided by 1. So I get 1.688. Round it off. Okay? Okay. It's a fairly simple reaction. So we've got N2O4 gas yields 2 NO2 gas. And the K is equal to 4 times 10 to the minus 4.
-4.
Yeah. Okay. What are we given? 1 mole sample of N2O4 is placed in a 10-liter vessel. So what's the concentration?
1.
Moles per liter, right?
Yes. So 1
Right? 1 mole in 10 liters?
Yeah, okay.
Okay.
I was thinking backwards. I was thinking it was still 10 instead of dividing by 20.
So we have 0.1 molar to start with and no NO2. So that means it's going to the right. And the change is 1 to 2. So what's the question? Calculate the equilibrium concentration of N2O4 and NO2. So it doesn't matter. We're going to do both of them. We can just make this one, let's make this one X. So if it's going that way, we're going to lose that much and produce this much because it's 1 to 2. Right? Okay. So this is going to be 0.1 minus X. This is going to be 2X. So that expression, well, that value is equal to this expression, NO2 squared divided by N2O4. And that means that this value is equal to NO2, 2X squared divided by 0.100 minus X to the first power. Okay. Now, if we go ahead and keep all of our X's as is, this one's going to come over here and give us an X term over there. But then we're going to have an X squared term here that has to come over there as well to make the quadratic, and then we'd have to use the quadratic. But notice that K is very small. It's going to produce very, very small amounts at equilibrium, which means wherever X is associated with some other real number, it's not going to influence that concentration very much. So in this case, we can approximate this one. I'm going to go ahead and multiply this out. 2X squared is 4X squared. 2X quantity squared is the same as 4X squared, right? And we're going to say that this x is too small to be considered. So that means we're left with this one in the denominator. Now, if we say multiply both sides times 0.1, that means this one is going to be 0, 0 times 0.1 is 10 to the minus 1, right? So 10 to the minus 1 multiplied by both sides, this will make 10 to the minus 5 on that side. And that's equal to 4x squared. Then x squared is equal to 4 divided into this one. Right? Divide both sides by 4. So that means x squared is equal to this one divided by 4, which is 1.00 times 10 to the minus 5th. And x is equal to the square root of that one. So 1 exponent take square root. I get 3.16 times 10 to the minus 3. 3.16 times 10 to the minus 3 for x. Right? So if that's x, what is the concentration of N2O4? Well, we didn't do our 5% rule yet. In order to do the 5% rule, we've got to know what this value is and that value is based on this value. So 0.1 minus 3.16 times 10 to the minus 3. And this one is 2 times 3.16 times 10 to the minus 3. So this one would be 6.32 times 10 to the minus 3. And this one would be, I could guess, but let's find out exactly. Would be 9.68 times 10 to the minus 2. Molar. So those would be our answers if we satisfy the 5% rule. So let's plug these values in, equilibrium concentrations, into this expression and see what it comes up with. So NO2 is this one squared divided by this one and that would be 6.32 exponent, change the sign, squared, and then 9.68 exponent, divide, and I get 4.12 times 10 to the minus 4 versus 4 times 10 to the minus 4. Okay, so let's see if that's 5%. So it'd be this one minus that one. Since they're both going to be this is times 10 to the minus 4. And this is 4 times 10 to the minus 4. Those cancel. We can just use this expression. So it's 0.12 divided by 4. That's 3%. So we can use those answers. Now let's see. What does the slide say? Okay. 0.097. Yeah, 2 places. 1, 2. 0.097. And this one is 6.32 times 10 minus 3. Okay? We just had to be sure that we were under 5%. All right, let's see. Le Chatelier's principle. This is the one I was referring to earlier when we said add a component on the reactant side for one scenario, add a component on the product side for another scenario, what would happen? Well, Le Chatelier's principle tells us that if you start at equilibrium, any equilibrium system, if it's disturbed, will respond in such a way as to accommodate that disturbance. So one way to say that is, if you add a reactant, it's going to shift toward products to use up some of the reactant and reestablish an equilibrium. Let's see how they say it. If a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that tends to reduce that change. Okay. So it responds to an insult. The discussion we've had so far was in terms of concentration. So those are fairly easy to rationalize. If you shift the concentration higher on the reactant side, it's going to move toward product. If you shift the concentration higher on the reactant side, product side, it's going to move to reactant. But there are other situations where we can cause a disturbance, and they're not as, the changes are not as evident. For instance, temperature. Since equilibrium, the K value is wholly dependent upon the temperature. If we change the temperature, that is a disturbance, and the system must respond to it. So this one, the temperature, we've already talked about concentration. For temperature, we need to know something about the system's enthalpy. Is it an exothermic or an endothermic reaction? So here's the way I look at it. For temperature, if you have this situation in equilibrium, C plus D, it all depends on which side the heat comes out. Does the heat go in here, or does the heat come out here? So, and we use an abbreviation for that heat is delta H. So if it's an endothermic reaction, heat is being added to the reactants to make products. Okay, endothermic. So the way, if you write it like this, then that means heat is a reactant. So if you add reactant, you're going to get product. So if it's at equilibrium and you increase the temperature, you're adding a reactant. And in endothermic reactions, when you raise the temperature, they go toward product, because heat is considered a reactant. The converse is exothermic reaction. In an exothermic reaction, we're producing heat as a product. So if you put heat on the product side and you increase the temperature, which direction are we going? Going back toward reactants. Okay? All right, so the other scenario is where you're dealing with gases. Or not dealing with gases for that matter. If you change the pressure in the vessel that contains your reactants and products, what effect will it have on the reaction? Well, if the system is such that A plus B equals C plus D, no effect. Because there's no change in pressure. You got the same number of moles reactants as moles product. That means there's no change in pressure. Remember, PV over NT, PV over NT are gas laws. If N is constant, it drops out of the equation, right? For our combined gas law, if N is constant, then it has no effect on the equation. So if you have the same number of moles before as after, then there's no effect on the equilibrium at all. But if A plus B is less than C plus D, if you have fewer moles before than after, let's use an example. Let's do that, this one. And you have N2 plus 3H2. There we go. For this real world example. In this case, you start off with 2 moles and you end up with 4. So if you increase the pressure, say, how would you increase the pressure on this vessel? Decrease the volume. Just squeeze it. You increase the pressure, then these 4 moles of gas are going to respond by producing fewer moles so that we alleviate some of that pressure that's being applied. Okay, so increasing the pressure on this one will drive it that way. Decreasing the pressure will drive it the other way. Okay, does that make sense so far? Okay.
To an added stress, if reactant or product molecules system respond to an added stress. If reactant or product molecules are added to a system at equilibrium, the system will shift toward the side opposite of the added component. If a reactant or product is removed, the system will shift toward the side of the removed component. Let's consider an example of a system at equilibrium, the reaction between iron and thiocyanate to form iron thiocyanate. Iron 3 is a light-colored ion in neutral or slightly acidic solutions. Thiocyanate is a colorless ion in solution. The iron thiocyanate complex is a blood red ion. The reaction of iron and thiocyanate in solution is reversible. That is, it moves in both the forward and reverse directions. Let's consider what happens to the reaction when changes are imposed on the system. In which direction will the addition of iron 3 nitrate shift the equilibrium of this reaction? Observe what happens as iron 3 nitrate is added.
Based on that reaction, it goes to the right because we added more iron to the system.
The equilibrium shifts toward the product since the iron 3 nitrate is a source of iron 3 ions, one of the reactants in our equation. As a result, more of the iron thiocyanate ions are formed and the solution turns redder.
Okay, we have one more.
The equilibrium between dinitrogen tetraoxide and nitrogen dioxide is dynamic. As shown, N2O4 molecules fall apart at the same rate that NO2 molecules recombine. If we change the equilibrium conditions, the equilibrium concentrations will shift according to the Chatelier's principle. As we increase the temperature, the equilibrium shifts to the formation of additional NO2 molecules.
So what does that mean? If it shifts to the right based on that equation, and we've added heat, it must be an endothermic reaction because we've added reactant and pushed it to the right. Correct? Let's draw it on the board. N2O4 yields 2NO2. So they said if we increase the temperature, it moves toward this, right?
Yes.
Okay. So that means that when we increase the temperature, we added it on this side. Because if it's the other way, if it were exothermic and we had heat added this way, it would go back the other direction. So we can tell from that experiment that this is an endothermic reaction, qualitatively. We can't tell how much, but we know that it is endothermic. I think that's the last slide. Yep. Okay, so next. Review document. Yeah, you have a review document that gives you practice doing all this stuff. You also have homework that should give you some practice. But the value of the review document is to give you experience. I mean, you know from last semester that how my questions look a lot like a review document. Right? So if you at least take a glance at it and see what type of questions I'm likely to ask, then even if you've done all your homework, then this should give you an idea. And it'll also tell you what's going to be on useful information.
Yeah. I noticed that.
Okay, since we don't have a lab today, the lab from last time will be due next week. Yeah. And I don't have anything else. Call it a short day if you want.